Okay, so we're reviewing derivatives here in preparation for your exam. And what we observe is that the derivative has four different meanings. The first meaning, physics, the instantaneous rate of change of f of x with respect to x at x equals c is called f prime of c. Second, on a graph of f of x, f prime of c is the slope of the line tangent to the graph of f at x equals c. And in particular, the tangent line can be constructed as y equals f of c plus f prime of c times x minus c. And the important thing is not to confuse x and c here. I get a whole lot of people giving me f prime of x. Don't do that. Then, in terms of formal mathematical definitions, we have f prime of c equals the limit as x goes to c of the difference quotient, that is delta y, f of x minus f of c, over delta x, x minus c. And the picture here is again that I fix a point c, and I go out a small distance to a point x, and I find the slope of the line between these 2 points, and now I take the limit as x goes to c, and as I do, this secant line becomes a tangent line. I can do the exact same computation but with different labels by writing f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. Which definition should I use? Whichever one is easiest. What is the here? The equation for the tangent line? So if I have a curve, y equals f of x, and I want the equation for this line right here, this is the line, y equals f of c plus f prime of c times x minus c. Because it goes through the point c comma f of c, and it has a slope of f prime of c. So if I use my point slope law, y minus y1 equals slope of x minus x1. Yes, sir.
So first
is on graphs. So this is commonly used in physics situations. This is used when I'm looking at a graph. And this would be analytic, both of these. It's all mathematical. Okay? Now that I know what a derivative is, how do I compute a derivative? It turns out that computing derivatives has less variety than computing limits does. The go-to tool for computing derivatives is our derivative rules.
I forgot to turn my spraying lap, and I found this is the homework I was talking about, and I had it.
So, thank you. So, the go-to tool for computing derivatives is the derivative rules, and we have at this point derivative rules that cover all of our basic families of functions. Think through those families of functions. Polynomials, you can find the derivatives, rational functions, trig functions, inverse trig functions, everybody's favorite, exponentials, log functions. We can do all of those, right? If you can prove them, you won't forget them. Yep. Now, under what circumstances would I want to do anything else? Well, only if I'm looking at a function that is not one of my elementary families of functions. So, For example, if I have a piecewise function at the joint, then I would have to use the limit definition. And by the limit definition, of course, I mean either one of these guys right here. This is a last resort, and I do this only if I need it for a particular situation, such as a piecewise function at the joint. So, for example, if I have f of x equals x squared for x less than or equal to 1 and 2x minus 1 for x greater than 1. And I now ask the question, what is f prime of x? Now let's examine this question here very carefully. We're looking for the derivative of f with respect to x at any point x. And we can see there are three different regions we need to worry about. X is less than 1, x equals 1, the joint, and x is greater than 1. For x is less than 1, my function is f of x equals x squared, derivative rule. So I can say that for x is less than 1, my derivative is simply going to be the derivative of x squared with respect to x, which is 2x. Likewise, for x is greater than 1, my function is 2x minus 1, and the derivative of that is 2. No problem. But right at x equals 1, where the two pieces come together, here and here, like so, it is entirely possible that my derivative could have one value from one side and a different value from the other side. So I will need to compute left and right hand derivatives separately. So at x equals 1, I have to compute the derivative from the left at 1 and the derivative from the right at 1. For the derivative from the left, I take the limit as x goes to 1 from the left of f of x minus f of 1 over x minus 1. Here I chose the limit as x goes to c definition because it's most convenient for me. You might make a different choice. For x's that are less than 1, what is f of x? X squared. For x equal to 1, what is f of 1? 1 squared. Not x squared, but 1 squared. Yep. And this limit you probably can do in your head by now because we have enough experience with limits. Check the form, 0 over 0, found the factor, find it, cancel it, let x go to 1, what value do I get? 2. Yep. Isn't that nice? There's the limit.
Why don't you just put in 2x and x equals 1? I bet you already got it. There it is.
Because I have no guarantee that my derivative at the joint will be the same as the limit as x goes to 1 of f prime. Those are not necessarily the same. And all I have to do to do that, and when we're done with this, I'll come back and show you an example.
Well, when we talk x equals, no, x is less than and equal.
Yes. No, and that's my whole point. Right at the joint, where x is equal to 1, I have different behavior on either side of 1, and the tangent line requires the same behavior on both sides. So I don't have a derivative rule that covers a function whose domain ends right here and then a new domain starts up. See what I mean? So that's why I have to consider the joint separate. It's a good question. And it's a question that requires some special care and feeding. Now, for x is greater than 1, what is f of x? 2x minus 1. But now, what is f of 1? Still 1 squared, yes. But when I simplify, good things happen. Because I get the limit of x goes to 1 of 2x minus 2, which is still 2. What conclusion can I draw since f prime from the left of 1 and f prime from the right of 1 are the same value? Nope.
What was the question?
What can I conclude from the fact that the derivative from the left at 1 and the derivative from the right at 1 are the same value?
So
Nope.
0 to 1.
Yes, I can conclude that the derivative is equal to 2. Not continuity, that's the limit, not the derivative. Right? And nothing about the limit of f prime, which is completely different. It's just that f prime of 1 is equal to 2. So therefore, that allows me now to go back and put in, I can put in an equal sign on either feature. And what allows me to put in this equal sign right here is because I checked f prime from the left and right.
Also, before you check it.
Yes, that's right. Now, just to answer Jennifer's question, and I think your question too, let me change the situation just a little bit, where I have f of x equals x squared, x is less than or equal to 1, and 2x plus 2 for x greater than 1. And all that I did was to change the intercept of this line right here. Now my function looks like this. And f prime of x is now equal to 2x for x is less than 1, and 2 for x is greater than 1. And at x equals 1, my derivative fails to exist. How do I know? Because f is not continuous there. And differentiability implies continuity. Therefore, f cannot possibly be differentiable because it would be continuous, and it's not. And if I were to compute the derivative from the right, that would back up my claim that f prime does not exist, because I would get 2x minus 2x plus 2 minus 1 squared all over x minus 1. And look at that limit. What is the form of that limit? Yeah, it's an infinite form. It's 3 over 0. This limit does not exist. Or equals plus infinity, however you want to say it. And therefore, f prime of 1 does not exist. Even though, Jennifer, the limit from the left of f prime and the limit from the right of f prime are both 2. So the moral of the story is that the limit of f prime is not the same as f prime at that point. Okay? Yes?
Function does not exist. That also means it's not continuous like that.
Yeah, right. So a function can have a derivative if it doesn't have a pointer. Yeah. Okay, so that's it for finding derivatives using our analytic tools. What about from a graph? The basic skill here is that we have some kind of graph of f. And now what we'd like to do is to sketch the graph of f prime. And using, now that you have some experience with your theorems, this should be really easy to do. To sketch the graph of f prime, we consider first of all the critical points of f, places where f prime is 0, or f prime fails to exist. What do we call this feature on the graph right here? A corner, that's right. And what do we call that? Horizontal tangent. In places, sometimes it's helpful to do an f prime number line. Places where we have a corner on the number line, are going to be marked with an X. Places where we have a 0 horizontal tangent on F are going to be marked as zeros on F prime. And then we can look at F and see that it is decreasing, increasing, decreasing again.
So every horizontal numbers are very discontinuous.
You just said two different things. Points of horizontal tangency on F are critical points where F prime equals 0. Critical points of the first time.
Oh,
Points of non-differentiability on F are points of critical points of the second time. Yes. Now coming back to the graph of F prime, I'm going to make sure that the graph of F prime goes through 0 at this critical point, is negative over here, and is positive over to here. Right at the point where my function has, actually it looks pretty close to 0, looks like it goes up. Right at the point where my function has a sharp corner, where f has a sharp corner, f prime abruptly changes values. Because the derivative from the left has one value, and the derivative from the right has a different value. And so on the graph here, my derivative, f prime, will have a jump discontinuity because f has a corner. In fact, let's lay those features out. If f has a horizontal tangent, then f prime, then f prime will be 0. If f has a corner, then f prime has a jump discontinuity. And the reason for that is that a corner literally means that f prime from the left at C is different from f prime from the right at C. If my graph of f has a vertical tangent, then the graph of f prime will have a vertical asymptote. Why? Because f prime at C is infinite, either plus infinity or minus infinity. And likewise, if my graph of f has a cusp, then the graph of f prime will also have a vertical asymptote. But whereas for the vertical tangent case, my vertical asymptotes will have the same sign from both sides. In the cusp case, my vertical asymptote will have opposite signs from both sides. And the reason for this is that for a cusp, my derivative from the left and the right are different signs of infinity. Well, we've almost finished up our graph of f prime. The only thing we haven't handled is this piece of the function right here. And this piece of the function right here is the shape of a straight line, which means its derivative will be a constant number. And therefore f prime will be horizontal. Notice that now we know about concavity, we can check our derivative a little bit. Check this out. Notice that f is concave up all the way from here to here. F is concave up. Therefore, I expect f prime should be increasing all the way from here to here. Look at that. It is. Cool. And f is concave down from here to here. So I expect f prime to be decreasing, as it is. And f is concave neutral. That is, f double prime equals 0, or a straight line, from here to here. So that f prime is neither increasing nor decreasing, but constant. So our concavity should follow our graph of f pretty well. Yes?
we have to know how steep the slope is.
No, I'm not too interested in that. If you do, you would obviously need a grid, right, to work from, and you would draw yourself a tangent line at a particular point, etc. How are we doing so far? Do you have a question?
How can we know this is
Calculate up.
common?
Corner? Oh, how did I see that it was there was a corner here? Yes, the thing that you're looking for is an abrupt change in direction. So look at the difference between a horizontal tangent, where my curve is smooth like that, and a corner, where my function is sharp, like that.
What about
Cusp, very similar. Cusp is going to have vertical tangency, the curve goes straight down, and then it will abruptly turn around and have vertical tangency again from the other direction, go straight up. So from the left, in this particular case, f prime from the left is minus infinity, curve goes straight down, and then it changes and goes straight up. Yeah.
For the f prime, how do we know where y is going to actually be 0?
Here, how did I know it was that far up? Yeah, that was what Clara asked. It's just a sketch, so you don't necessarily have to. Since this point of inflection here is the point of maximum slope, you could draw yourself a tangent line here and find the slope of that tangent line, and that would give you the value of f prime there if you wanted to know how high they are. Yes.
so the cusp over here?
Uh-huh.
Should, or if on the left side, should I go and go on that?
So, so this is f, and these are the implications about f prime. So don't try to match this to this. Instead, you want to visualize f as having a cusp at x equals c, such that from the left, we go straight up, and from the right, we go straight down. So this would be the corresponding graph of f that leads to this graph of f prime. You're welcome. Any other questions?
So yes, opposite side for cusp.
Opposite signs of infinity for cusp. Finite opposite signs would give me a corner, and the same sign of infinity gives me a vertical tangent.
Vertical tangent C on the from the C, and
Not limit, derivative.
derivative from the left and derivative from the right. As C.
Take a look at this f prime. This is f prime, right? And this f prime goes to infinity from both sides of C. What this means is that my curve is going to go straight up and have an infinite rate of change right here. But then, as I move to the right of C, its rate of change decreases, and I smooth out like that. So a vertical tangent looks just like this. And this graph of f produces that graph of f prime. Better? Okay. Well, lastly, the thing that students always want to forget, and I tell them not to forget, and they forget it anyway, don't be that guy. Don't forget that your calculators can find derivatives for you.
The use calculator.
On half of the test you can. Remember that we can always find a derivative with second calc dy dx at a specific point. And the process is very simple. Let's say you're working on a calculator section, and you have y equals e to the square root of sine squared t, and for some reason you need y prime of 1, something like that. Do I really want to take the derivative using my derivative rules? No, this is awful. I would never want to take the derivative of that thing using my derivative rules. Instead, I would let y1 equal e to the sine of t, sine of x squared and I would use second calc dy dx to find the derivative at x equals 1. And all that I would say is, all that I would do is to report out that value to how many decimal places? 4. Just like that. A very simple, straightforward procedure, and please don't use derivative rules to find the derivatives of complicated functions when you don't have to.
Where did root? Still root.
What's that?
Where did still root?
Oh, I just put it in there. Oh, where did it go? Huh? Yeah, you got to enter the right function. You're right.
How question how do we find the absolute value?
If you hit math num, the first option is absolute value.
Oh,
Okay.
thank you.
Also in that section is int, if you need the int function. Okay, so much for finding derivatives. Now what do we do with them? The most important thing that we can do with derivatives at this point is to find rates of change in real-world problems. The biggest use we had for this was describing motion along a line. So we had position, s, velocity, s prime, and acceleration, which was v prime, or s double prime. And we had a large number of words that we used to describe the motion. Let's see if we can remember all those words. What does it mean to say that an object is stopped? Velocity equals 0. What does it mean to say the object is moving to the right? What about moving left? Yep. How about speeding up?
Accelerating the velocity.
Good. And now that you guys know the chain rule, I can show you why that is. What does it mean? What does the term speed mean? What is the speed of an object?
Absolutely.
Absolute value of velocity. So speeding up should mean that my velocity is my speed is increasing, right? In other words, it should mean that the derivative of my speed is greater than 0. Well, what is the derivative of my speed? If I take the derivative of the absolute value of the velocity, then what I get is velocity over absolute value of velocity times the derivative of the inside. But what is the derivative of velocity? Acceleration. And if I require that my derivative of speed be greater than 0, then what that's telling me is that v times a divided by v divided by speed is 0. Is greater than 0. This term right here is always positive, so I don't need to consider it. When I multiply two things together and get a positive value, what do I know about them? They have the same sign. So that whenever my speed is increasing, that is, sorry, when the derivative of my speed is positive, the velocity and acceleration necessarily have the same sign. Yes, sir?
If we give you a previous speed, we can get acceleration.
Can you get that information out of there? You can't actually, because if I give you the speed, you don't know whether that speed refers to this direction or that direction. So speed really takes the velocity and strips the direction information out of it. Okay, so these were the most common rates of change problems, but we also had rates of change problems where, like water, the height of water is given by blah, blah, blah. How quickly is water coming in? Let's do one of those. totally made this function up. And now we might ask two questions. At what time is the tank empty? And the second question might be, at what rate is the water decreasing? I should say the height of water decreasing at t equals 1. So this is a typical kind of real-world problem in which we might use derivatives. And our basic approach to these is going to be to model with math by translating from English into math, carrying out the appropriate analysis, and then answering in English. That's the basic plan. If I were in Korea, I would be answering in Korean, and then I would be in trouble.
What is the meaning?
Other problems? I don't know.
Just calculate.
I don't know. Okay, so at what time is the tank empty? How do I represent the tank being empty in that? That's exactly it. I represent that as h of t is equal to 0. And now we just carry out the analysis. It means 3 minus t squared is equal to 0, which means t is equal to how come we didn't consider negative root 3 either? There was an implicit assumption, right? The assumption was an assumption about the domain. Yeah. And is that always a safe assumption? No, not necessarily. We would probably need that domain assumption supplied to us. Okay. So there it is. And so we would say, we would now respond in English. The tank is empty at t equals root 3 hours. If you had a calculator on you, you might have computed that as 1.713. I forget the root. I forget what 3 exactly. Whatever that is. At what rate is the height of water decreasing at t equals 1? Translate this into math form. What are they asking about? At what rate is the height of water decreasing? You've got the right concept, but we're not going to call it velocity. Instead, we're going to talk about it in the terms of this problem. How do we say what he's trying to say? There it is. What's that? H prime of, but at what point? At t equals 1. So notice the two elements here. Because it is talking about a rate of change, we're automatically going to translate that as a derivative. And because they are asking about t equals 1, we're going to translate that as the derivative at t equals 1. This is what we're trying to find. Then, we compute that derivative either using derivative rules or using the calculator. If we have calculator available to us, we can directly find h prime of 1 on the calculator, and we give a value. If we do not have calculator available to us, then we calculate number 7. But we need to package our answer in the terms of the problem. And again, we reach back to the problem to find that language. So we would begin by saying, how about just the water is decreasing at a rate of, the height of the water is decreasing.
-2 meters per hour.
Meters per hour, but adjust to, that's right. We have the right units. Here, we do not want to include the negative sign because we already took care of it with the word decreasing. And then finally, what's the last thing? That's equal to 1. Be specific. And that's it. That's how those questions are answered. Okay. In addition, we also can use our derivative to find equations of tangent lines. We don't have any uses for tangent lines yet, but we will in January. So we're going to kind of hold this in reserve. So for example, if f of x is equal to x squared, find the equation of line tangent. How about the lines tangent and normal? That are parallel to y equals 6x minus 1. Something like this. You guys remember these problems. And so now I observe that I want my tangent line. I can't have a normal be parallel. So the line tangent parallel to y equals 6x minus 1. The normal would be what? Perpendicular to y equals 6x minus 1. So I have a line tangent that I want to be parallel to this line. That gives me some information about the slope of my line. How can I translate the tangent parallel to 6x minus 1? Or in general, f prime of x is equal to 6. That's my translation. There's the slope of my tangent line. There's the slope of my given line. Should be parallel, they must be equal. But now what this tells me is the unique point where my line tangent will be parallel. And I recommend drawing a picture so we can see what's going on. 6x minus 1 is going to come down like this. And I'm looking for the point where the line tangent is parallel to it. And that happens around x equals 3. Does that make sense? Well, I have a slope, I have an x coordinate. The only thing I need is the y coordinate for my point. How do I find that y coordinate?
Original.
Into f of x, that's right, and I get 9. So I have a slope of 6, and I have a point, 3, 9, and therefore I can say y equals f of 3 plus f prime of 3 times x minus, and we're done.
The region is y minus 1.
Right, it's the same. The most common mistake is that people try to use f prime of x, and they give me some equation in terms of x, or some formula in terms of x for f prime. No, not that. We're looking at a specific point, and therefore we have a specific slope, a numerical value of the slope. Does that help? The rest, and we're out of time, but the rest of it is all about curve sketching, and you guys have been doing that a lot for the last week, so I'm going to let that ride. The homeworks that you have passed in, I can mark up and get back to you, I hope by 3. So come find me in the computer lab if you want those back to help you study. Yes, sir?
So now, f prime of x means slope has to be constant.
What I mean is that the slope here will be the slope at the specific point of tangents.
It has to be a constant angle.
It has to be a number.
And you just took that
Or it
from
has to be in terms of the point of tangency is the best way to say it. Yeah.
You just took that from the other equation.
Yes.